In this video, I want to talk about the electric field due to an electric dipole. So recall that an electric dipole is created by having two charges, so 2 point charges of the same magnitude but opposite charge. So one negative, one positive. And so in this setup, we have it in a coordinate system, and we want to find the electric field at this point right here, whereby it is right in between, such that the distance is d, so it's 1/2 d in the middle, and some arbitrary distance on the y-axis. What is the electric field at this point? So let's first figure out some basics. So what is the electric field due to one of the charges? Well, since they're both the same, both have the same magnitude, and so we can say that they both have kq over r squared in terms of the electric field. And in order to find this, it's best that we start by looking for symmetry. And so what's nice about this is that we're trying to find the electric field in between, so right in the middle. So we can draw these electric field lines as I have drawn here. And we'll see that from the positive charge, it goes out to here, forms an arrow for the electric field, and has a positive y and a negative x component. Likewise, for the negative charge, we have it points inwards towards the charge, but it also has a negative x component, and then different from the positive charge, it has a negative y component. And so as we can see, then we can, by arguing by symmetry, in that the electric field point that we are trying to find is in between both of them, the y components of the electric field will cancel. And so we will only be left with the x component. And the x component we can expect to be pointing in the negative x direction. So thus we would have to put a negative sign. So let's solve for this. So E sub x, and in fact I'm going to drop this x just to avoid confusion, because we know that the net electric field will only just be in the x direction, negative x direction. So the total E net will be equal to the E due to the positive charge and the E due to the negative charge. So E positive plus the E negative. So the electric field due to the negative charge, oops, that should be a negative. And we're going to use some symmetry here. So we're going to define angle theta here, and that means that if we draw this triangle separately here, with the positive charge here, and r distance away and theta here, that means that this negative x component would be the electric field due from r distance away times sine theta. So that would be the negative x component. So let me erase that, or you know what, I'll keep it there. So E due to, it'll be a negative sign because it's in the negative direction. So negative the magnitude from E sine theta minus, or actually I'll put it's plus a negative, so due to the negative charge in the negative direction, and the theta is the same thing, it's magnitude of the negative charge sine theta. And so what does this give us? You see here we have kq over r squared for both of them, and that means that the total is negative 2kq, so 2q for the two charges, times sine theta over r squared. Conversely, you can write out the k. Sometimes they'll write it as 2q, so negative 2q sine theta over 4 pi epsilon naught r squared, right? It's the same thing. 1 over 4 pi epsilon naught is k. So without further ado, let's continue. And let's make sure that we understand what we are trying to find again. So E is equal to negative 2kq sine theta over r squared. Now, this is a bit confusing. We have a theta component and we have an r component. But oftentimes when we're going to solve these questions, we won't be given an r. We'll only be giving a distance away from these from the dipoles, and we also won't be given a theta. So it's quite arbitrary, to be honest. So we want to solve this kind of without those variables. And so just like how when we solved for the electric field due to a line of charge, we are going to have to use some geometry or trigonometry. So over here, I'll draw out the triangle again from the positive charge. This side will be d over 2, and this side will be r. And then this side will be that arbitrary y direction kind of length. So an arbitrary y in the positive y direction, and that means y squared plus d over 2 by Pythagorean theorem is equal to r squared. And therefore, that also means, so we'll call theta over there, sine theta is equal to d over 2 over r. So we have all our components. We have r, or we would have to take a square root of y squared plus d over 2 squared, and all square root. And this gets quite lengthy, but we will see the derivation leads to a nice form that we can use to extrapolate something more meaningful. So let's plug this in. So we got r, we got d over 2, and we got r again. So this comes out to negative 2 k cubed. So, we have our charge components. Then let's separate this. Let's first write out the 1 over r squared component. So it will be 1 over the square root of the square of the square root. So we're going to cross that out and just get y squared plus d over 2 squared. And that gives us r 1 over r squared. And then times sine of theta. And sine of theta would be d over 2 divided by the square root of y squared plus d over 2 squared, right? And where did I get this square root? It's r, because sine theta is d over 2 divided by r. And so let's clean up this kind of mess we have here. And it becomes, and recall that p, not p, we don't need that. So let's see what we can cancel out here. We can cancel out this 2, right? And that seems to be about it. So let's write it out. We get negative qd divided by, and so we have essentially a square of a square root and a square root. So we get basically 3 over 2. So I'm going to write out this thing, 3 over 2. And I should write the k right here, forgot that. And y squared plus d over 2 squared. So that should be everything. And so this is our E field at an arbitrary y away from the center of a dipole. And so let's make an interesting argument here. Let's say y is significantly greater than d. We will then see that this bottom component becomes y squared to the 3 halves, which becomes y to the third. And thus we can say that if the point we are talking about is really far away from the dipole, so far away enough so that d is fairly small, we can just make the argument that it's proportional to y over y cubed. My bad, I lost my words. So that's a pretty important concept. Just understand that the E field will then just be a kind of proportional. So proportional to 1 over y cubed. So just know this derivation and you will be good.